Electric vehicles are often considered a cleaner alternative to gasoline cars, but there is still a major problem hiding inside them: batteries. Manufacturing conventional lithium-ion batteries requires energy, mining, and materials such as lithium, nickel, and cobalt. That has created growing interest in battery technologies that could be cheaper, safer, longer-lasting, and less dependent on scarce minerals. And one startup believes it may have a completely different answer. Instead of building a battery around traditional metals, the company PolyJoule has developed a battery that relies on conductive polymers, essentially advanced plastic-based materials that can store and release electrical energy. So, could a plastic battery actually compete with lithium-ion technology? The answer becomes interesting when we look at what PolyJoule is targeting. Unlike lithium-ion batteries designed primarily for compact devices and vehicles, PolyJoule's technology is aimed mainly at large-scale stationary energy storage. That means applications such as renewable energy systems, industrial facilities, data centers, and critical infrastructure. This is important because solar and wind power are naturally intermittent. Solar panels produce electricity during daylight, while wind turbines depend on weather conditions. Batteries are therefore needed to store electricity when production is high and release it when demand increases. PolyJoule believes its polymer-based chemistry could offer several advantages in this market. One of the biggest is durability. The company has claimed that its batteries could achieve roughly 12,000 charge cycles. If achieved in commercial operation, that would represent a major advantage over many conventional lithium-ion systems, which typically operate for far fewer cycles. PolyJoule also claims its batteries can deliver very high bursts of power. According to the company, its system can discharge around 1 megawatt of power within seconds. Fast response is extremely valuable for the electrical grid because sudden changes in electricity demand can happen almost instantly. The company has also reported charging times of less than 5 minutes under certain conditions. That would make the technology particularly interesting for applications where energy needs to be absorbed and delivered rapidly. But perhaps the most important difference is the chemistry itself. Traditional lithium-ion batteries depend on materials that require mining and refining. PolyJoule's technology instead uses conductive polymers and a water-based manufacturing process. Because the battery does not rely on lithium, cobalt, or other conventional battery metals, the company says its manufacturing process can avoid some of the environmental and supply chain challenges associated with traditional batteries. The manufacturing process is another important part of the story. PolyJoule has demonstrated production using roll-to-roll processing, a technique already used in other large-scale manufacturing industries. The company says this approach could eventually allow polymer batteries to be produced without the extremely controlled clean room environments required for some advanced battery technologies. That could potentially reduce manufacturing complexity and cost. And cost is critical when we talk about grid storage. For renewable energy to become more reliable, battery storage needs to become significantly cheaper. PolyJoule has indicated costs around the tens of dollars per kilowatt-hour as production scales, although actual commercial costs can vary considerably depending on manufacturing volume, system design, installation, and market conditions. Safety is another area where polymer batteries could have an advantage. Lithium-ion batteries contain flammable electrolytes and can experience thermal runaway if severely damaged or improperly managed. PolyJoule describes its chemistry as inherently safer and says its batteries do not require the same level of fire mitigation infrastructure as conventional lithium-ion systems. The company has also stated that its batteries are highly recyclable because they are based largely on polymer materials rather than large quantities of conventional battery metals. If these claims hold up at large commercial scale, the technology could offer an attractive combination of long life, rapid response, safety, and lower dependence on mined materials. But there is a major limitation. PolyJoule batteries currently have much lower energy density than lithium-ion batteries. That means they need significantly more physical space to store the same amount of energy. For a smartphone, laptop, or electric vehicle, that is a serious disadvantage. Nobody wants to carry a battery several times larger simply to achieve the same driving range or operating time. This is why PolyJoule is not trying to replace lithium-ion batteries in every application. Instead, the company is targeting locations where size and weight matter much less. Imagine a large battery installed beside a solar farm. It does not need to be small enough to fit inside a car. It simply needs to store electricity safely, deliver it quickly, survive thousands of cycles, and operate for many years. That is where the plastic battery concept becomes much more compelling. And this could become increasingly important as renewable energy expands. Solar and wind installations can produce huge amounts of electricity at certain times of the day, but that electricity is not always generated when consumers need it. A durable, safe, low-cost storage system could absorb excess electricity and release it later, helping stabilize the grid. This also opens the door to another possibility, replacing some of the short-duration storage systems currently used for daily grid balancing. Conventional lithium-ion grid batteries are often designed around several hours of storage. Polymer-based systems could potentially be configured for longer-duration applications where safety, cycle life, and cost matter more than compact size. However, that does not mean the technology is ready to replace lithium-ion batteries everywhere. Moving from a laboratory or pilot system to large-scale commercial deployment is one of the hardest challenges in the battery industry. The technology must prove that it can maintain performance over thousands of cycles, operate reliably under different temperatures, meet safety certifications, and remain economically competitive after manufacturing, transportation, installation, and maintenance costs are included. And that is where PolyJoule's next stage becomes especially important. The company has been working toward commercial systems that can demonstrate whether its polymer battery technology can move beyond the laboratory and into real-world energy infrastructure. The real opportunity for PolyJoule may not be replacing every battery on the market. It could be solving a completely different problem, storing large amounts of electricity safely and economically for stationary applications. Think about a data center. These facilities require enormous amounts of electricity and cannot afford interruptions. A storage system that can respond almost instantly could provide backup power, stabilize voltage, and help manage sudden changes in demand. The same concept applies to hospitals, factories, telecommunications infrastructure, and other critical facilities. Renewable energy projects could also benefit. A solar installation may generate more electricity than the grid needs during the middle of the day. Instead of wasting that excess energy, a battery could store it and release it during the evening when electricity demand rises. This is one of the reasons long cycle life could be so valuable. A battery used every day may experience hundreds of charge and discharge cycles each year. Over a decade, that can add up to thousands of cycles. If a battery can survive significantly more cycles without major degradation, the economics of the entire energy storage system can change. Instead of frequently replacing expensive battery packs, operators could potentially keep the same storage system running for many more years. PolyJoule's rapid response is another advantage. Grid operators do not always need batteries simply to store energy for hours. Sometimes they need a system capable of reacting within seconds to stabilize the electrical network. A battery that can quickly absorb or release large amounts of power could therefore serve as a tool for balancing supply and demand. This is particularly useful as more solar panels, wind turbines, electric vehicles, and other variable electricity sources are connected to the grid. But there is still one question that could determine whether PolyJoule becomes commercially successful. Can it produce these batteries cheaply and at enormous scale? Battery technology is filled with promising laboratory breakthroughs that never become mass-market products. The chemistry may work. The prototype may perform extremely well. But commercial success requires something much harder: reliable manufacturing, predictable costs, long-term durability, certifications, financing, supply chains, and customers willing to deploy the technology. PolyJoule, therefore, has to prove its system under real-world conditions. If it can demonstrate thousands of cycles, stable performance, competitive pricing, and reliable operation for years, the technology could become an interesting alternative for stationary energy storage. And this is where the comparison with Tesla becomes especially interesting. Tesla has already built a major energy storage business around products such as Powerwall and Megapack. These systems rely on lithium-ion battery technology and are designed for homes, businesses, and utility-scale installations. PolyJoule is taking a different route. Instead of maximizing energy density, it is prioritizing characteristics such as safety, cycle life, rapid power delivery, and reduced dependence on conventional battery metals. In other words, the two technologies do not necessarily have to compete in exactly the same way. Lithium-ion batteries remain extremely useful when space and weight are critical. That is why they dominate electric cars, phones, laptops, and many portable devices. But when the battery is sitting inside a dedicated facility, energy density becomes less important. A utility company may be perfectly willing to use a larger battery if that system is safer, lasts longer, and costs less over its lifetime. That distinction could give polymer batteries a real opportunity. There is also a broader environmental argument. As the world builds more batteries, demand for raw materials will continue increasing. Mining and refining lithium, nickel, cobalt, and other materials can create environmental challenges and expose manufacturers to volatile commodity prices. A battery chemistry that reduces dependence on these materials could help diversify the energy storage industry. However, it would be a mistake to assume that a plastic battery automatically means a zero-impact battery. The polymers still have to be manufactured, processed, transported, and eventually recycled. The environmental benefits will ultimately depend on the complete life cycle of the technology. That is why real-world data matters more than impressive laboratory numbers. If PolyJoule can demonstrate that its batteries remain reliable after thousands of cycles, operate safely without expensive cooling systems, and achieve competitive lifetime costs, then the technology could become much more than an interesting experiment. It could become part of the next generation of renewable energy infrastructure. And the timing may be particularly important. Global electricity demand is increasing as transportation, heating, industry, and computing become increasingly electrified. At the same time, renewable energy is expanding rapidly. That combination creates a massive need for energy storage. We may therefore see a future where there is no single battery technology dominating every application. Lithium-ion could continue powering vehicles and portable electronics. Solid-state batteries could eventually improve energy density and safety. Sodium-ion could provide a lower-cost alternative for certain applications. And polymer batteries could specialize in long-life stationary storage. That may actually be the most realistic future of batteries, not one technology replacing everything, but different chemistries being optimized for different jobs. For PolyJoule, the opportunity is clear. Its batteries do not need to beat lithium-ion in every category. They simply need to be better where stationary storage matters most. If they can provide long cycle life, rapid power delivery, competitive costs, and strong safety performance, they could find a valuable place in the rapidly expanding energy storage market. But there is still a long road between promising technology and widespread commercial adoption. The next few years will reveal whether PolyJoule can scale production, reduce costs, and prove its performance outside controlled demonstrations. And if it succeeds, the impact could extend far beyond one startup. A new generation of safer and more sustainable batteries could help renewable energy become more reliable, reduce pressure on critical mineral supply chains, and provide electricity networks with the flexibility they desperately need. The most important question is no longer whether batteries can store electricity. They clearly can. The real question is which battery chemistry can store that electricity for the lowest lifetime cost while remaining safe, reliable, and environmentally responsible. And PolyJoule believes plastic-based batteries could be part of that answer. One of the biggest limitations of PolyJoule's battery is also its greatest clue about where this technology belongs. The current cells have an energy density of roughly 60 watt-hours per kilogram, far below the level offered by modern lithium-ion batteries. In other words, storing the same amount of energy would require a much larger and heavier battery pack. That makes this technology unsuitable for smartphones, laptops, electric cars, and other applications where compact size and low weight are critical. But that does not mean the technology has no future. In fact, PolyJoule appears to be targeting a completely different market: stationary energy storage. This includes data centers, industrial facilities, heating and cooling systems, renewable energy projects, and critical infrastructure where safety, durability, and rapid power delivery can be more important than compact size. The company has also designed its systems to operate across a wide temperature range, potentially allowing them to function in demanding environments with minimal capacity loss. This could make polymer batteries particularly interesting for large-scale energy storage. Think about how the electricity grid works today. Solar panels produce huge amounts of electricity during the middle of the day, while demand often increases later in the afternoon and evening. Wind power can also fluctuate depending on weather conditions. Battery storage helps bridge this gap by storing excess electricity and releasing it when the grid needs it most. Today's lithium-ion storage systems are already playing an important role in this process. Tesla's Powerwall and Powerpack, along with other large-scale battery systems, can store electricity and provide power during periods of high demand. However, conventional batteries are not necessarily designed for extremely long-duration storage. This is where technologies like PolyJoule could become interesting. Because the polymer chemistry is designed around safety, long cycle life, and high power operation, these batteries could potentially be used in applications where a large battery footprint is acceptable. The company has suggested that its systems could provide much longer duration energy storage than conventional installations, potentially reaching around 20 hours depending on the application. If that capability can be demonstrated economically at commercial scale, it could become valuable for renewable energy. Imagine a large solar farm producing excess electricity throughout the day. Instead of allowing that energy to go unused, a large polymer battery system could store it and release it later when demand rises. The same principle could apply to wind farms, industrial facilities, hospitals, data centers, and other critical infrastructure. Another interesting possibility is seasonal energy storage. Today, storing electricity for days or weeks remains a major challenge. Storing renewable energy across entire seasons is an even bigger challenge. If polymer-based systems can eventually demonstrate extremely long-duration storage at competitive costs, they could become part of a much larger solution for balancing renewable electricity generation. But there is an important reality that should not be overlooked. A promising laboratory technology is not automatically a successful commercial product. The transition from prototypes to mass production is one of the hardest stages in battery development. A battery must survive thousands of cycles, operate safely in different environments, remain affordable, and perform consistently when produced in enormous quantities. PolyJoule still has to prove that its technology can meet those requirements outside controlled testing conditions. The company has reportedly produced thousands of cells using roll-to-roll manufacturing, which is an encouraging sign, because scalable manufacturing is essential for reducing costs. The next major milestone is even more important, moving from development toward real commercial deployments. If the company can successfully deliver larger systems and demonstrate their performance in real-world environments, the technology could gain much more attention from utilities, renewable energy companies, and industrial customers. And that is ultimately what makes the plastic battery concept so fascinating. It is not trying to replace lithium-ion batteries everywhere. Instead, it could occupy a market where lithium-ion batteries have limitations. Electric vehicles need extremely high energy density. Smartphones need small batteries. But stationary energy storage can afford larger and heavier systems if they offer better safety, lower cost, longer life, and easier recycling. That distinction could be critical. The future of batteries may not be dominated by a single chemistry. Lithium-ion could continue powering cars and electronics. Sodium-ion could serve lower-cost applications. Solid-state batteries could eventually improve energy density and safety. And polymer batteries could become another important option for large-scale energy storage. The most successful battery technology may therefore depend less on having the highest energy density and more on being optimized for the job it needs to perform. PolyJoule's plastic-based approach is still developing, and there are plenty of unanswered questions about its long-term economics and commercial scalability. But the idea itself challenges one of the biggest assumptions in modern battery technology, that better batteries must rely on increasingly complex metal-based chemistries. If conductive polymers can deliver high power, survive thousands of cycles, avoid flammable materials, and eventually reach lower production costs, they could open an entirely new path for grid storage. And as renewable energy continues expanding, that could become extremely important. Because generating clean electricity is only half the challenge. The other half is figuring out how to store it safely, affordably, and reliably until people actually need it. That is where batteries like this could eventually make their biggest impact. So, what do you think? Could plastic-based batteries become a serious competitor to conventional lithium-ion storage? Or will their lower energy density prevent them from becoming commercially important? Let us know your thoughts in the comments below. If you enjoyed this video, don't forget to like it, share it with others, and subscribe to the channel for more updates on electric vehicles, battery technology, renewable energy, and the future of clean transportation. Thanks for watching, and we'll see you in the next video.